Good evening, students. How are you? So make sure the screen is visible to you and I'm audible to you. Firstly, if it is so, please put this message in the chat box. Okay, for my confirmation. Hi, Anjana. Hi, Rajesh. How are you? Am I audible to you? The screen is visible to you? If it is so, please put this. Okay. Okay, got it. You can use this reaction also. Thank you, Anjana, for the confirmation. Is there any event in your JNV for today or yesterday? Yesterday, I think there was an event in JNV. That is why you guys have left so early in the previous lecture. In the last 15 minutes, there is no student there. And do not do that. Okay? Because if you left the lecture in the middle or somehow when 35 or 40 minutes has been passed, so take it or only for 20 minutes is remaining. Okay? So do not do that. Okay. Anjana, Shri, and Rajesh, you are a very attentive student. I have seen. So it's for your good, na? So we will wait for 1 or 2 minutes more. See if other joins, and if they not, then we will start our topic. Okay. So meanwhile, you will tell Anjana, Shri, and Rajesh from which JNV do you belong? Okay, JNV Nizamabad. Got it. And you also from JNV Nizamabad. Okay. And the reason for you guys are Hyderabad, na? Or Shillong. Hyderabad. Got it. For Rajesh, it's Hyderabad, and obviously for Anjana, it's also Hyderabad. Okay. Hi, Samsung Tab 2. What's your name? What's a good name? Samsung Tab 2. I think that is not your name. What's your name? Good evening, by the way. Mamata. Okay. But some days you have joined with this name, na? You have changed your device, I think. Because I have seen this name. पकड़ लिया ना मैंने. I got you. So I welcome you all in this lecture. Mamta, are you from JNV Nizamabad also? And if not, what's your JNV? Okay. So these students are from JNV Nizamabad. Got it. So we are on lecture number 3 of the chapter mechanical properties of solid. And in Avanti module, you find the name as elasticity and viscosity. Okay. So do not worry about that name. Just focus on the concept that you are learning. Okay. So the chapter name in NCERT is also, it is mechanical properties of solid. So we are on lecture number 3. Before I will talk about this lecture, what we have covered, we will talk on that. So in the previous session, we have learned about all the types of stresses and all the types of strain. So mostly there are 3 types of strain and 3 types of stress. There are 3 types of elastic moduli also based on that theory. So 3 types of stress: longitudinal stress, shear stress, and bulk stress, or you can say hydraulic stress. And based on that, 3 types of strain we have studied: longitudinal strain, shear strain, and bulk strain or volumetric strain. Okay. So now we are going to learn about some topic. Yeah. We are going to learn about Young's modulus, shear modulus and bulk modulus, Poisson's ratio, elastic potential energy in a stretched wire, and application of elastic behavior of materials. This, I think we are not going to see this. Only these 4 topics we are going to cover. Okay. So we will start the lecture. And please be comfortable. Okay. If you have anything in your mind, like you are not happy with the strategy of teaching, you are not, I'm not saying happy, but like it is not more comfortable for you. So in that mean I am talking about. So please make sure that you need to be comfortable with that. Okay, I'm not forcing you. So if you're not comfortable with that strategy that we are teaching, or you more concept, more questions, okay, that we will discuss in our weekend classes, so you can join there. But in this scenario, if you want more animations, more pictures and all, because I think that you're not a kid anymore. Okay, although we have to keep a kid inside us, but if I talk practically, you are not a kid anymore. Okay. So if I just attract you by showing some animation, showing some videos, so this will not help you out, I think, because the more valuable thing that you have from a chapter is a concept, is the learning behind it, because that is the only thing that going to help in your examination when you are sitting in the examination. Or okay, the examination somehow will help you, but the concept that you have learned, the formula that you have learned, that will going to help you directly. So be practical and be a man, like uh yeah, we don't need this, we need the concept. Okay, I'm not saying that I cannot put the ammunition and all. I can put, and I have put whenever it required. But do not just rely on these ammunitions at all. Okay, because in the end, the concept that you have done is going to help you in your examination in solving questions. Okay, and just try to find out your aim. What's your aim? Your aim is not to identify these ammunition or this ammunition I have seen in that chapter or no. No. Your aim is to crack the examination. Okay. And for cracking the examination, you need more and more practice. Okay. That is in the end going to help you. So try to solve more and more question. Try to learn more and more concept rather than fact. Okay. So whenever we finish the chapter, try to understand what you're learning inside it, what you have learned, what concept you have learned. Got it? Now, is this clear to you? What I have told, what I have told you? Okay. Please be responsive now. So our very first topic is, yeah, got it. Thank you, Anjana. Our very first topic is the Young's modulus. Now, what you are thinking, what is Young's modulus and all? Now, modulus of elasticity, firstly, you have to understand. It is just the ratio of stress and strain. Okay. Like modulus of, or let me change the screen. So, just a second. Yeah. The modulus of elasticity is nothing but the ratio of stress to the strain. Okay. We have learned that stresses are of three types. Strain is also three types. So based on that data, we can say this model of elasticity will be also of three types. Okay. Now, so the ratio of stress to strain is called modulus of elasticity. Simple. Now, modulus of elasticity is of three types. The first is Young's modulus, shear modulus, and bulk modulus. Okay. Now, what is Young's modulus? So, I have told you that three types of stress we have, three types of strain we have. If we take one of the stress, one of the strain, that ratio is the Young's modulus. If you take longitudinal stress ratio with the same strain, which means longitudinal strain, okay, that ratio is termed as Young's modulus of elasticity. The ratio of longitudinal stress sigma, longitudinal strain, that is epsilon, is defined as Young's modulus and it is denoted by a symbol capital Y. Okay. Yes. Now we have applied a force. We have changed the dimension of this rod by delta L. So strain you will know. Here we are going to write the stress. Stress is nothing but force per unit area, restoring force per unit area, and we have replaced the restoring force with the applied force divided by the area of cross section on which this force is acting, which is given as A. Now, what is strain? Strain is the change in dimension divided by original dimension. In longitudinal strain, it is just the ratio of change in length divided by the original length. So change in length is nothing but delta L and original length is nothing but L. So this is the Young's modulus of elasticity. Okay. This Y is equals to F by A divided by delta L by L. What is the SI unit of it? Since you know that this delta L by L, which is strain, it has no dimension. It is a dimensionless quantity. So only Young's modulus will depends on the stress, and stress has a dimension of Newton per meter square, or you say Pascal. Okay. Now we have different types of material. We have iron, wood, aluminium, polystyrene, glass, and copper. The modulus of elasticity means Young's modulus of elasticity vary for different types of material. It is not same for all the materials because there is different types of elasticity that each and every material will follow. Okay, you can see the data. For steel, the Young's modulus is 200 into 10 raised to the power 9. That is not written here, but it is multiplication with 10 raised to power 9 Newton per meter square. The yield stress it can bear is 250 10 raised to the power 6 Newton per meter square. Means If you will see the data, the maximum value of Young's modulus of elasticity for steel, and maximum value of yield stress is also for steel, which means if you talk about this, y is nothing but the stress upon strain. The higher the value of y will denote that if you kept this sigma as constant, which means, and to increase y we need to decrease this epsilon, which means for very large value of stress, these materials having a very small value of deformation. That is why the Young's modulus of elasticity is large for steel, because if you apply the stress, it will get very less stressed. Okay, very less deformation it will show to you. That is why the bearing capacity of the steel is very high. Okay, it can bear a whatever the load, है ना? Very high value of load it can bear. Now, why steel is preferred in heavy duty machines and structural design? This is the question for you guys. Why? In each and every scenario, you will see the steel is used. And also for the suspension of any vehicle, we use steel. Now you are thinking that rubber you can stretch more, so rubber would be more elastic. No. Elasticity you have to understand. Elasticity is nothing. Elasticity is not about that how much it can get stressed. Elasticity is not about how much it get, और it के जगह हम लिखेंगे how much the material get stressed. No, it is not that. So what is elasticity? Elasticity is something that told us that how much stress it can bear for the value of deformation. Okay. Now, you know that for rubber, I will take rubber and steel. This is steel. For rubber, you know, when you apply a little bit a value of stress, it will get stressed, which means it shows you no resistance to the deformation. But can you stretch the steel like you can stretch the rubber? No, because it shows you, it offer you a very high resistive force with a very small value of deformation. That is why we can say that the steel is more elastic than rubber. And that is why it is being used in the suspension system. Got it? Because whatever the load we applied, it get very little bit of stretching in steel, which means it can take that load on. Okay? And having a very small value of deformation. Got it? Now I think it is clear to why we are using it in a structural design. Because in structural design, you will say the very heavy load is applied on the steel. So if it gets stressed, then the structural stability will not be there. But we know that steel is much more elastic, which means it can bear a very large value of load with a very small value of deformation. That is why we are using it as a structural design and heavy duty machines, because it has a very high value of the Young's modulus of elasticity and yield strength. Okay. The Young's modulus of elasticity For steel is very large, therefore this material requires a large force to produce a small change in length. And for this reason, we prefer steel to be used in heavy duty machine and the structural designs. If you can compare it for copper, take the same dimension. We have take 5 centimeter length of this rod. Area is same. Force applied that is Fs, which means Fs in steel and in Fc in copper. Young's modulus of steel is 200 into 10 raised to the power 9 Newton per meter square. And for copper, it is 110, 10 raised to the power 9, 9 Newton per meter square. Now you can see that you can calculate y f upon a delta L by L. So we can see that for a very small value of deformation, which is 0.005 centimeter, and the same deformation we have given to this, we will see that how the force will vary for this. If you do the calculation, the force for steel required to deform it for 0.005 centimeter is 2000 Newton, which means 2 kilonewton load you have to apply. But for copper, if we will see, only 1100 Newton force is required to give it the same deformation as steel. Okay, which means steel has more elasticity. Okay. Now, we can say that steel is more elastic than copper. In this question, a copper wire of length 2.2 meter is given to you, and a steel wire of length 1.6 meter, both of diameter 3 mm, are connected end to end. When stretched by a load, the net elongation is found to be 0.70. Obtain the load applied. So there is a copper wire and steel wire. Okay. Or both have the same diameter, means same area they have, area of cross section, and connected to the end to end. One of the end is connected to the steel with one of the end of copper wire, and they are elongated with a force or load, you can say, and total elongation is 0.70. Now you can easily say that by the logical explanation that we have given earlier, that copper will get more stressed instead of in respect of steel. Okay. Now you will see length is given to you. Length of copper is 2.2 meter. Length of steel is 1.6 meter. Area is same. We have calculated this. Now, if you talk about the deformation, delta L of copper plus delta of L of steel, total is given to you 0.70 mm. So the copper and steel wire are under the same tensile stress that is given you in the question. Now, load upon area equals to YC into delta LC over LC. Now, we have used a formula for Young's modulus of elasticity. And for that, we have got the ratio delta LC by delta LS is equals to YS over YC into LC over LS. Now, we have calculated this value, and it is give us that delta LC means deformation is copper is 2.5 times of in steel. Now, totally have given one of the value is this equation we have provided, and this equation we have already given. So two equation, two variable, we can calculate the value of delta L and delta C, and based on that we can calculate the value of applied load, which is 176.625 Newton. Now, this is a very important concept, and you must pay attention to this, because this is in your practical also and in your JEE main syllabus also. Okay. So be careful attention. We are going to determine the Young's modulus of elasticity of a particular material of a wire. Okay. By a experimental setup. So for this experimental setup, we have taken a fixed rigid support. Two wires A and B are hanging from that. One of the things that you would note that the wires are identical in nature, which means length of wire A is equals to length of wire B equals to capital L, and radius of wire A is equals to radius of wire B is equals to small r. So both the wires are identical in nature. Now this wire A we have taken as the reference wire, and another wire we have taken as the experimental wire. Okay. Why we have taken two wires, this will also be clear to you. This is the meter scale on which we are going to measure the elongation. This is clamped with this support, and this support will also have some load so that the wire will be in a straight line position. While we wire will be this wire also will be a little little stressed. Okay. Now this is the vernier caliper or vernier scale which is attached to this wire B with a pointer P. Okay, this is the pointer. So what will happen? The load is present in both the. Now we are going to increase the load in experimental wire. So what will happen? Because of this load, a tangential stress will be developed in this wire. So this wire will get elongated. And when it get elongated, the the vernier scale will move on the meter scale, and we will note that readings. Okay, so that we will note that how much this experimental wire it gets stressed with respect to this reference wire. So this will getting stressed. So with the help of this pointer, we are able to measure that how much this experimental wire is getting elongated with the help of these loads. Now, and the difference between the reading will give you the elongation. So difference between two vernier reading, initially we will know the reading, and finally we'll also, after the elongation, we will keep the reading. Then we take the difference of that. Suppose initially we have a reading 1, okay, and finally we will get a value of 1.8. So what we will say, we will take a difference of this 1.8 minus 1. So zero point 0.8 will be the elongation. Okay. Now, you got this? If you have any kind of doubt, you can ask. Now, let M be the mass that produce an elongation delta L in the wire that we have put in this wire, experimental wire B. So applied force would be mg, total mass, into gravitational acceleration. Now, with the help of this Young's modulus of elasticity, y is nothing but sigma, which is stress, divided by epsilon. Now, we will know all the value. Mg we will know the radius of this wire. So we can calculate this pi r square divided by epsilon. Delta L we have not with the help of vernier scale, and L original length we have already known. So all the data are known to this. By putting them, we would calculate the value of Young's modulus of elasticity. Now, the question arises that in your mind that we can do it for one scale also, one wire also. Why do we need the another wire? So why do we use two wires? So the two wires is used because if there is a change in temperature, so because of the change in temperature, the thermal stress will develop in the wire. So reference wire we have kept for this purpose, so that if any change due to temperature will be there, so we will compensate this change in the final reading. Okay. So that is why we are using two wire setup. Okay. Because reference wire is used to compensate for any change in length that may occur due to change in room temperature. Since any change in length of the reference wire due to temperature change will be accompanied by an equal change in experimental wire. Okay. Suppose initially they are at 1 meter. Okay. Both the wires, but due to temperature change, This will have a value of 1.8 meter, sorry, 1.1 meter. And finally, by the with the help of load, because the reference wire will only elongate with the help of this temperature change. We are putting the load on the experimental wire. So experimental wire will get stressed. Suppose let's say 1.8. So final reading is not 1.8 minus 1. Final reading will be 1.8 minus 1.1, which is 0.7 meter. Okay. So that is why we have used two wire. One of the wire for temperature change, one of the wire for length that may change due to room temperature, and one of the wire due to load. Now, shear modulus and bulk modulus. Similar, shear modulus is the ratio of shear stress to the shear strain. Now, it is represented by D, and it is also called as modulus of rigidity. Now, we can say that G is nothing but shear stress divided by shear strain. Shear stress is nothing but force parallel per unit area divided by shear strain is nothing but X upon H, which you can generally say this X upon H is theta for small deformation. So it is F upon A upon theta. Okay. Now you can say that this G is equals to F upon A upon theta. F upon A is nothing but shear stress. So sigma S is is equals to G into theta. So you can see here the Hooke's law is valid, which tells us that stress is directly proportional to strain. So in this case, shear stress is directly proportional to shear strain. And this removing this proportionality constant will result in this. This proportionality constant is nothing but G, which is shear modulus of elasticity or modulus of rigidity. Okay. So you can see that F upon A upon delta X over L. This you can replace all the thing I have told you. Now, SI unit is same, Newton per meter square, because theta is dimensionless quantity or Pascal. Some of the data are given to you. Obviously, steel wheels has the maximum value of shear Young's modulus and maximum value of shear modulus. Okay. So this data is for Young's modulus. It is for Young's modulus, and it is for modulus of elasticity. Okay. Now, so it can be seen that shear modulus or modulus of rigidity is generally less than Young's modulus. Okay. Now, this question we are going to do. A cube of side 4 centimeter is fixed at one end. A tangential force of 4 into 10 raised to the power 5 Newton is applied at the other end. Calculate the twist produced in the cube if the modulus of rigidity is 6 into 10 raised to the power 10 Newton per meter square. Now, given F is equals to 4 into 10 raised to the power 5 Newton. This is the tangential force that is given to us, or parallel force. Area is also given to us. G is also given to you. You can see here, G is also given to you as 6 into 10 raised to the power 10. Okay. Now, F is given to you, area is given to you, G you have to calculate. Theta. Now, theta only the thing that you need to calculate. This is F upon GA. Put the values and get the answer. So this is in radian. If you want to convert it into degree, so you have to multiply it with pi upon 180. Then finally you will have as 0.238 degree. Got it? Now, next question. In this question also, a square lead slab of side 50 centimeter and thickness 10 centimeter is subjected to a shearing force on its narrow face of 9 into 10 raised to the power 4 Newton. The lower edge is riveted to the floor, which means fixed to the floor. How much will be the upper edge be displaced? Which means in this, X has been asked. Suppose this is the slab. This is the slab you have, and you apply the shear force on it, and it will get slightly above, slightly shifted. So this shift X has to be asked in this question. So we'll try to solve it now. So this is the force. This length is 50 centimeter and this width is 10 centimeter. Okay. And the force is applied on the narrow face, which means on this face, not on this face. Okay. Because narrow face is this. You can see. Now, area is given you as 50 into 10 raised to the power minus 2 into 10 into 10 raised to the power minus 2. You can calculate 50 centimeter is given. So you have to convert centimeter into meter. 10 centimeter, again you have to convert it into meter. Area is nothing but length into width. So we would multiply this length with width. Area is given to you. Now, area you will have 0.05 meter square. We know that G is nothing but shear stress by shearing strain. So F upon A upon delta X by L. Only delta X has been asked to you. So delta X is equals to FL over AG. You have all the values, put them one by one, and you will have the answer. So it will get shifted with 0.16 mm. Now, bulk modulus. So the bulk modulus is nothing but, again, we have three types of stress, three types of strain. Based on that, the modulus of elasticity is also three types, and we are dealing with the third type. So definitely, by the name it suggested itself that bulk modulus is nothing but the ratio of hydraulic stress, or one of the name, volumetric stress, you can also say it. One more name is this. You can say it, instead of hydraulic stress, it is bulk stress. So the ratio of hydraulic stress slash bulk stress slash volumetric stress to the corresponding hydraulic strain slash volumetric strain slash bulk strain is called the bulk modulus, and it is denoted by a symbol capital B. So here you will see on this object a uniform pressure has been applied, which has a direction passing through the center of it. Radially it has been applied and perpendicular to each face. This pressure is acting perpendicular to this object, okay, but uniformly. So it will going to decrease the volume of it, and let's say the decrease in volume is delta V. No. B, we know that bulk modulus is nothing but the ratio of hydraulic stress to the hydraulic strain. So B you can say minus P upon delta V by V. Since B is a positive quantity, B is the positive quantity. P pressure is also positive, but you will see that this pressure will result in decreasing in volume. So this decrease in volume will be a negative quantity. So to compensate this negative, we put a negative sign in front of this expression, because delta V is already negative. So to make this be positive, we have provided a negative sign in front of them. Okay. The SI unit is same, Newton per meter square, because delta V by V is the same quantity ratio. So it will be a dimensionless number, or Pascal. The negative sign indicates the fact that with an increase in pressure, a decrease in volume occurs. So we have to maintain the value of bulk modulus to always positive, and for that we have put a minus sign. We know that the reciprocal of bulk modulus is called compressibility, and it is denoted by K. So K is nothing but equals to 1 by B, and 1 by B is we have already calculated. B is nothing but delta P divided by delta V by V. We can go the upper place. So B will be V delta P divided by delta V, and if we take the reverse of it, inverse of it will become 1 upon V delta V by V into 1 upon delta V. This delta V by V is nothing but the fractional change of volume. This delta V by V is the, you can say it is the fractional change of volume. Fractional change of volume. Okay. Which says us that upon increasing for how much value of change in pressure, how much fractional change in volume has been occurred. Okay. So it is also defined as the fractional volume change per unit increase in pressure. This is delta P, and this is fractional change of volume. So some of the bulk modulus is given to you. You will know that bulk modulus for solid is greater than bulk modulus of liquid. These are liquids. These are solid. So we can see that solid, liquid, and gas. Bulk modulus of solid is greater than the bulk modulus of liquid, and the bulk modulus of liquid is greater than the gases. So these are nothing but gas. It is a gas. Air is a gas. So based on that, since compressibility is the inverse of bulk modulus, so this relation for compressibility will be reversed. You will see that compressibility of gases are greater than liquid, and liquid ki compressibility is greater than solid, which you can easily identify. You can easily compress the gas, but for compressing a liquid you put a dedicated effort, and for solid it is very hard to press them or compress them. Got it? So gases are a million times more compressible than solid, because the you will see the atoms in this scenario, you will see the atoms are very closely packed. So when you are going to compress, this atom will have no space to be shifted. Okay, that is why you are not capable enough to compress this. Got it? But if you talk about this gas, we know that very few particles are there. So if you're going to compress this gas, this particle or this particular atom has a very far space to be covered when it get compressed. So it has a entire volume, I'd say, enough volume to be adjusted. So that is why the compressibility of gases are larger than the solid. Now, this is the question. The Marina Trench is located in the Pacific Ocean, and at one place, it is nearly 11 kilometers beneath the surface of water. The water pressure at the surface of trench is about 1.1 times raised to the power 8 Pascal. A seal ball of initial volume 0.3 meter cube is dropped into the ocean and fall to the bottom of the trench. Now, what is the change in volume of the ball when it reaches to the bottom? Bulk modulus of water is given to you, and density of water is also given to you. Now, Why is this change in volume will occur? Because the pressure will increase if you increase the depth. And as this ball going to the marina trench, which is 11 kilometer beneath the surface, you have increased the depth, so the pressure will increase. That change in pressure will get a change in volume of that ball. Okay. Now we know that if this is 11,000 meter, which means 11 kilometer, initially the water at the surface, pressure at the surface, which means the atmospheric pressure, or some of the pressure we have 1.1 into 10 raised to the power 5, 8 Pascal. Now this ball is dropped and it reaches at this 11,000 meter. Since you have that, the volume has been changed. Now it is given that bulk modulus of the water is 2.2 into 10 raised to the power 9 Newton per meter square, and initial volume is 0.32 meter cube. Now pressure at this height will be atmospheric initial pressure plus rho gh. We move h height below in a density of liquid rho, the pressure at the end will be rho gh. Now you can calculate this. Initial P node is given to you 1.1 into 10 raised to the power 8. Rho gh, rho is 1000, g is 10, and h is 11,000. Now pressure, you have got it. Now bulk modulus is equals to minus of pressure or change in pressure, you will say, divided by delta V by V, change in volume by volume. Now delta V is nothing but minus of PV by B. All the values you have now. You can calculate the change in volume, which is minus 0.032 meter cube. Okay. I hope you got this question. Now we are dealing with Poisson's ratio and elastic potential energy in a stressed wire. Now, what is Poisson's ratio? So firstly, we will understand the concept. Now, since there is a rod, let's say, okay, and we have applied a tensile force to this. So what will happen? This will elongate. This rod will stretch somehow. But we know that the volume, because we are not adding mass or removing mass, only force has been applied. This length is L, and let's say this length is L dash. So we will definitely know that L dash is greater than L. But we know that the volume that it has initially will be same because there is no loss of mass. So volume final will be equals to volume initial. For volume final, it is pi r square L, which means the area into initial, final area into length final. Volume initial is also initial area into final area, final length initial. Now we know that initial length is nothing but L, and final length we have as L dash, and we know that L dash is greater than L. So this final area should be less than this initial area. Why? So that you could maintain this volume constancy. Okay, and area is nothing but pi r square, which means the final radius would be decreased with the initial value. So as this, in the direction of force, if a one dimension is increasing, so a perpendicular direction, this dimension will decrease. Got it? To compensate the volume constancy, to maintain the volume constancy. So the dimension have been changed in transfer direction. Then the ratio of this change, the ratio of this transfer strain to the longitudinal strain is termed as the Poisson's. This is all about the Poisson's ratio. Got it? Now, just a second. I hope you got the concept of it. We have length L, force has been applied. So it has decreased in this dimension, transfer direction, and length has been increased, area has been decreased. So the strain perpendicular to the applied force is called lateral strain. So the ratio of lateral strain to the longitudinal strain in a stressed wire is called Poisson's ratio. This strain perpendicular to the applied direction of force. Force has been applied in this direction, so it is perpendicular. So this strain is also termed as transverse strain, and another name is lateral strain. Okay, and the ratio of transverse strain to the longitudinal strain is termed as Poisson's ratio. Original diameter of wire is d, let's say. Contraction of the wire in the dimension of this diameter will be delta d. So lateral strain will become delta d by d. Poisson's ratio is nothing but lateral strain to the longitudinal strain. This is the formula for Poisson's ratio. Since it has been a negative sign, because this delta d is negative in change. So Poisson's ratio can be negative. Now, it is also a ratio of two strain, and stress is a unitless quantity. So there is no value of dimension. Okay, so it is a dimensionless quantity. Pure number, no dimensional unit. Its value depends on the nature of material. For steel, you have this point. For steel, the value is between 0.28 to 0.30, and for aluminum alloys, it is 0.33. Now, elastic potential energy in a stressed wire. This is the final topic of this chapter. So when a wire is put, we are going to see how the elastic potential energy will vary for a stressed wire. So when a wire is put under a tensile load, the work is done against the interatomic forces. We know that. This work is stored in the wire in the form of elastic potential energy. Same as the spring. When we stress the spring, so we have done a work against the spring force. So that energy in spring will be stored as the spring potential energy. Okay. We have stressed this with this force F. So the change in length is L and original length is capital L. So we can say that force is nothing but YA into L upon L. This would be come from here. We know that force or stress is nothing but equals to Young's modulus of elasticity into strain. Sigma is nothing but F upon A. Y into epsilon is nothing but delta L by L, and delta L is given to a small l divided by capital L. So from here you can say that force is nothing but Y A divided by L into small l. Okay. Same as the spring force. Now, what we have seen, this force is depend on this length L. So this is not a constant force. So we are going to see for a very elemental change in length, what is the work done. So work done we will see for a very small change in the length. This is the elemental change you can see. Because this force is variable, it will depend on the value of deformation. So we have seen that dW is nothing but force into displacement. Displacement is in the direction of force. So that is why the sign is being positive. So it is FdL. We will put the value of L, which is YA small l over L into DL. Now to calculate for this entire length, we would integrate it from 0 to L. Okay. Or capital L you will say. Now for 0 to L we have calculated it. The work done is YAL into L square by 2. So we have W is equals to YAL square upon L into 2. Now this is the work done, but we know that this elastic forces are conservative in nature as the spring force. So when there is a conservative force, so we said that the potential energy is nothing but the work done by negative of work done by conservative forces. So we can replace the force that we have applied by the elastic force, that is a restoring force. So for that, we have multiplied with this in this equation 1 by 2 y L by L square. We have multiplied by L. You will see here W is equals to y a L square divided by 2 into L is nothing but the volume. This L by L, change in length divided by original length, is the strain. Okay. So you can see that the work done here is nothing but 1 by 2 times young. This work is stored in a form of elastic potential energy in the stressed wire. That is why this elastic potential energy per unit volume of the wire. So we can divide this volume with this work done. So what do we have? We have U is equals to 1 by 2 times sigma into E. And this U is nothing but the energy density. And you can apply it for any type of strain, which means if the strain is longitudinal, shear, or bulk, for each and every case you can apply this formula. Okay. Now we can see a question on that. Calculation of the work done in stretching a uniform metal wire of area of cross section 10 raised to the power minus 6 meter square and length 1.5 meter by 4 into 10 raised to the power minus 3. So we have stressed. This is the value of stretching is given to you. Young's modulus of the wire is also given to you. Simply we know that delta L by L we will calculate strain. Y is the stress about strain. So Y, from that equation you can calculate the value of stress. When the stress has been find out, you will find out the volume, because in work done, what should we need? We need 1 by 2 times stress into strain into volume. Okay. So in this equation, this is nothing but 1 by 2 times stress we already know, we have calculated, strain we have already calculated, volume we already know. So work done in scenario will be 1.061 joule. So this is it from my side. Okay. Thank you so much. If you have any kind of doubt, you can ask. Otherwise, the lecture is been over. Thank you so much for being attentive. Bye-bye. Take care of yourself.